Hello there, my name is George Mock, and I'll be your guide on this talk. The reason you should be listening to me is that I've been working at Texas Instruments for over 20 years, and during that entire time period, my job has had something to do with either C compilers, assemblers, linkers, and tools of that nature. We call tools like that, the name for the whole group of them, we call them the code generation tools. And this talk is code generation tools, tips, and tricks. And really what it is, it's the set of things that I wish folks knew when they were just starting out using Texas Instruments, C compilers, assemblers, and linkers. Now the first thing I want you to see is all the places I want you to go to when this slide set doesn't answer your questions. The first half of this slide is about the compiler wiki. This is a collection of articles on all sorts of different topics, and it's constantly evolving. People are constantly adding to it or tweaking it and things like this. This is where you can find all of the manuals for all of our tools. This is where you can find the link to download free compilers. There's an FAQ, things of this nature. If that doesn't satisfy your query, the second half of this slide talks about the compiler forum. This is where you go to post questions directly about what your situation is. I watch this forum on a daily basis. It's part of my job description. Questions are answered there. Discussions sometimes break out. And also it's searchable. Okay, so don't forget the idea of if you see some error message pop up, well, you can go search the text of that error message in the forum, and you've got a decent shot at finding it and finding an answer for what your situation is. So these are some great resources to bookmark. Second thing I want to try to pitch to you before I get into the meat of the presentation is actually take the time to read the Readme file that comes with the compiler. This talk here really only covers the highlights, and it's not always 100% up to date because things are changing all the time. The Readme will cover the features that are introduced in that release and usually in great detail. It takes you an hour, often less, to get through this Readme, and it's well worth your time. There are two main ways to get it. There's a download. This is the link for downloading free compilers, and that includes a link to just the Readme file, so you don't actually have to download the entire thing and install it and so on and so forth just to see the Readme file. You can go to that link and you'll see the Readmes. Now that's not true for all of our compilers. For instance, the ARM compiler is not there. So the other way you can go about it is to go into the root directory where your compiler is actually installed. Of course, there are a lot of places that could be depending on how you install the compiler and this kind of thing. But probably at the present time, the most typical thing is you have CCS v4 installed, and so your path will be something like what you see here, that C:program files and so on. Even in CCS v5, the one that was released a couple weeks ago, it's just going to be the root of CCS v5, then tools/compiler/ some target name, and that last line on the slide is C2000, C5400, that kind of thing. That's the directory for the specific target's compiler. And in that directory is where you'll find the Readme file. And again, it's well worth the time it takes to hunt this down and read it. You'll get critical detail there that can be obtained really nowhere else until it finally makes it into the books, often months later. So here's the agenda for the meat of the talk. The first part of it is the recommended development flow. That's where I get into how the compiler implementers think you're using the compiler. I say it that way because it's often a bit different as to how people actually use it in the field and practice. But it's interesting to see how the compiler is put together and how it's intended to be used. And some things that may seem a bit confusing at first make a lot more sense once you have this viewpoint. And that's also where I get into recommended build options and things of that nature. The next section of the talk is about just some basic tips and tricks on using the linker. EABI is a new thing coming down the pipe, and exactly what an ABI is and how EABI is a variant of it, and all this is a little bit involved, and so I'll get into that when we get to that part of the talk. Intrinsics versus assembly, those are two different ways of programming at a lower level than C, and different ways of going about it. and I'll compare and contrast those two and trying to give you TI's viewpoint on how to do that kind of thing. Types and alignment is probably the one area where people get tripped up the most when they start using TI compilers. Things like, what do you mean char is 16 bits wide, and what do you mean int is only 16 bits wide, and long's not 32 bits wide, and things like that. We'll talk about that there. 16 by 16 and 32 multiply, it's a very common operation. In DSP algorithms, there's a right way to go about it, and there's a wrong way to go about it, and we'll get to see both of them. Memory models talks about, there are a lot of, and it varies from target to target, but there's kind of like some base concepts behind memory models. Why do we have memory models, and what are the things that you do to activate the extended memory models, and what are some of the price you pay when you do that. Diagnostics, we're talking about the error messages, warnings, remarks, things like this that the compiler may emit when it's compiling your code. And what's worth knowing about those, and in particular, how can you use it to save yourself time during the development process? In addition to all the C compiler and assembler and linker stuff, there are a couple other utilities. I call them useful utilities. We at least hope they're useful. No, they typically are. The other things that you can do after you've built your code to extract information from it. And then the last little section is just tips that I'd like to pass on, but I couldn't find some way to package it in somewhere else in the talk, so there's like 3 or 4 things in that very last section. So let's start with the recommended development flow. So I'm going to give you a little bit of time to take this in. Excuse me. There we go. So you can see the flow sort of moves in a clockwise direction. Not too exciting. Probably the most important thing to realize is that we compiler implementers expect that you're going to debug your code, get it all working, so you compile with -G at first, right? And then you'll compile optimization. Okay, -G is the switch for, add debugging information to my object file so that I can debug it under CodeComposer. And -O says enable a large class of optimizations that I'll talk about here in a second. So what's important is to see that those things are separate. Why are those things separated? That's what this slide is about. Well, optimization versus debug, there's a trade-off there. As one gets better, the other one gets worse. Okay. Now, if you try and combine them together, which is a common operation in the field, I see this a lot. If you try and combine them together, what happens? Okay. Well, the first thing we need to talk about is the effects on debugging. Operations can be reordered. Okay. Just because you wrote A equals B plus C and then D equals E minus F doesn't mean they're necessarily going to happen in that order. Okay. With 2 operations like that, they're independent. Whether you do the first one as second or whatever, it doesn't really change anything. Now, this can be disconcerting when you're single-stepping through your code and things aren't happening in the order that you wrote them in your original code. Now, variables can be eliminated. Let's say you write a for loop for I equals 0 to 100, something like this. In a lot of cases, I will be eliminated. It won't even be there. And so if you try and ask through some debugger query or another, what's the value of I right now, it won't be able to answer because I was taken out. Okay. Now, effects on performance, the instruction scheduling can be impaired. It can't be as good as it would otherwise be. And the reason for that is when you build -G, one of the things that happens is the compiler emits these directives for making the mapping between a group of assembly language statements and the source line that it came from. Okay? And so if you look at it in some of the files, you'll see debug directive, a bunch of code, debug directive, a bunch of code. And that's fine for debugging, but for instruction scheduling purposes, this is bad because one of the things that happens is the compiler will not move an instruction past a debug directive. And so that introduces sort of artificial limitations on how far an instruction can move for scheduling purposes, and that's not something you want if performance is what you care about. If performance is what you care about, you want that instruction to go in the best spot possible no matter what, and you don't want to have to care about debug directives. Okay, so this last little part of the slide compares performance, and it's just one data point. Your mileage will vary on this a lot, okay, but I just want to give you, one data point just to give you something of an idea what it might be. So for on C6000 with an MP3 decoder, we discovered that building with just -O, the code runs 16% faster than if you run with -O-G. Okay, so that's just, like I said, just one data point. This slide talks about the optimization levels. This is just sort of basic information about optimization that's worth knowing. So remember, optimization is not enabled by default because, we compiler implementers presume that you're going to debug your code first thing, and that you're going to optimize it later. So it's not on by default. And then when you enable it, you can select from 4 levels, O0 through O3, and the primary difference between these different levels is, well, how much of the code is the optimization phase considering at once to make its decisions. And the more code it looks at one time to make its decisions, it will tend to make better decisions, okay? But the trade-off is the more stuff it's looking at one time, then the more stuff it's looking at one time, it's going to take a little bit longer. It takes a bit more, system resources on your host machine as you're compiling, this kind of thing, all right? So at O0, it tends to look at one statement at a time. You can think of it, it doesn't look across semicolons. As soon as it sees a semicolon, it forgets everything it knows and starts over again. Now, blocks, we're talking about, let's pretend you have an if and a little bit of code, then an else and a little bit more code. Those if and else's separate the code into blocks. Okay, a block is a group of statements that all execute together. A function's pretty obvious. It's everything inside a single function, and then O3, it's looking across function boundaries even, and all the way across a file. Optimization is critical, of course, if performance is something you care about. A particular point worth making is on C6000, the optimization that's most important of all is called software pipelining, and you don't even get any software pipelining unless you build it at least -O2. If you must build a debug, which is a common situation, then I highly recommend you also use -MN. Okay, this restores some of the lost performance. It doesn't restore all of it. It doesn't get you back to if you were building with -O without any -G at all, but it gets a lot of it back. It does degrade your debug experience, but most people find that it tends to be okay in practice. There's a wiki article about this. There's the full URL and the link. And it talks about this thing in more detail. This slide gives you a little bit of hints about how can I find out more about compiler options. Obviously, you can go look in the documentation, but this is something that you can do yourself. This is really aimed at command line users. If you're somebody who interacts with compiler only through CCS, this slide does not really apply to you, okay? Because I presume you're running from the command line. You can see this command right here, CO6X, and then you pipe it through more or less or whatever command I can use, and you can see a quick summary of all the options. If you're interested in any one particular option, you can say CO6X or change CO6X to whatever compiler you're using, CO470, whatever makes sense. You can say CO6X-H whatever option you're interested in, and you can get a bit more information about that option. Most of the options have some of this detail in there. A few of them don't. And another cool feature you can use, you can say CL6X-H and just a little bit of text, and it will search through the options, and anywhere you have a match on that text, it'll show you the options. And so this little last box here gives you an example, give you an idea of what I'm talking about. CL6X-H, everything related to debug, and it all starts coming out. I've been talking about compiler options. One detail I want to relate here is all compiler options have what we call a long form. Okay, the long form of the option starts with 2 dashes, and here's an example right here: --simdebug:_dwarf. Okay, many options, not all of them, many options have a shorter alias, and the alias for --simdebug:_dwarf is -g. Okay. The documentation and the Code Composer Studio build dialog emphasize the long form of the options. That's what you tend to see when you interact with the compiler and the books in that manner. In this slide set, I tend to use the short options because you're typically short on screen real estate, okay? So to avoid confusion, here's a table of all the options that are ever mentioned anywhere in this particular presentation. On the left is the short form. That's what the slides are going to show. This is what you'll, on the right, this is the long form of those options. That's what you're going to tend to see when you're looking at it in Code Composer Studio or in the documentation, things like that. So I've already talked about -g, I've mentioned -up, I've mentioned -mn. The rest of these will show up later in the presentation, but I wanted to collect them all together right here. Okay, so recommended build options, common question. You know, I'm a C6000 user. What are the best build options for me? Okay, well, here's a wiki article about that for C6000. For C55000, there's another one. Obviously, there are other targets that TI supports, and we don't have wiki articles for those, although we may have them, you know, in the near future. If you're, for instance, an ARM compiler user, these articles are still worth looking at. There's going to be some general ideas that are worth learning that can apply to your compiler. This slide is specific to C6000. A couple of things that are worth knowing if you're trying to get the most out of the optimization for C6000. There's a lot of information that the compiler would like to know about your code, but it tends not to know. And there are methods for you to inform the compiler about that stuff. And so what am I talking about? Pointers don't access the same memory locations. We use this fancy term called memory aliasing to describe this. If there's no memory aliasing present, we can typically do a much better job of constructing the software pipeline. Another piece of information the compiler would like to know is, well, how many times is this loop going to run? Okay, even if all you can say is it's always a multiple of 4, something like that, the compiler can take advantage of information like that. Another thing that can be helpful is pointers are aligned on 8-byte boundaries. This is something that can enable something we call SIMD, single instruction, multiple data optimizations. There's a wiki article that's referred to right here. Is the full URL, and there's a clickable link, which talks about all these things and how do you use them. And the way it works is there's this very simple example there, and in turn, each little thing is added to it. Most of these are little source annotations, okay? And you see the example get faster and faster and faster. This particular guy ends up running about 25 times faster by the time all the annotations are added. And it's really simple stuff if you know what it is and you know how to use it. So that's the purpose of that article. Okay, so that wraps up all the recommended development flow stuff, and we're going to move into a slide on linker tips and tricks. Okay, so the first thing worth knowing, and this tends to surprise a lot of beginners, is global variables are not initialized to 0. If you've got some, you say int global variable semicolon, In hosted systems, your laptop and your Linux box, what have you, when you do that, you can presume that global variable will have the value 0 when main starts running. That is not the case with TI compilers. Now, if you're building under EABI, it is the case. That global variable will be set to 0 for you. But that's not the dominant case these days. We are in the middle of changing that. But if you're not using EABI, which is going to be most of you, then you cannot presume your global variables are 0. The linker does not know anything about your system memory layout. Okay, it doesn't know where anything is. And so the way you inform the linker as to, well, this is what my memory layout is, you provide a linker command file that has what we call memory and sections directives in it. All these things are detailed in the linker documentation. The book is called the Assembly Language Tools User's Guide. Okay, and there's also in the compiler distribution in the lib directory, there's usually a file, lnk.cmd. It's an example linker command file. It's a good place to start. You typically get them anytime you get a board or something. Usually the person who supplies that board will give you the linker command file that corresponds to that board. So those are some sources for where you can get that kind of information. The linker has an option, -w. I forget the long form of it, -- emit warnings or something like that. It warns you when certain suspicious things occur. Okay, things that you may not even understand right now that could be a problem for you, but believe me, they can be. And if you link with -w, it'll complain about those and give you a chance to research it and figure out what's the story and what's the best thing for me to fix this issue. 3 of the issues are mentioned here. Creating a section without a specification. This typically happens when somebody made a spelling error in either the linker command file or often the assembly or wherever a section was created, and they don't match, and things go downhill from there. And the really bad part is things can end up in memory without you actually having any guidance over it, and that's something you never ever want to do in a production build. You definitely want to explicitly create your stack and explicitly create your heap, set them to the size that's correct for your system, and place them in the right kind of memory and this kind of thing. So if you don't do those things and you build a -w, you'll hear about it and you'll get a chance to correct the issue. Okay, I've mentioned EABI at least once already. Let's talk about this guy. All right, so the first thing I need to talk about is what is an ABI. ABI is a generic industry term, stands for Application Binary Interface. And it's this collection of conventions which allow separately compiled object files, libraries, to link together into a cohesive executable. And there's a lot that goes into it. I mean, one of the things that you have to agree on, of course, is the object file format, but you also have to agree on things like the first argument will be passed in the register R0, or whatever the convention is, and the second argument will be passed in some other register here, and then all further arguments will be passed on the stack. It's things like long is 32 bits, and type short is 16 bits, and all things of this manner. If you ever obtain an application binary interface specification and print it out, it's usually going to be around 100 pages at least, and sometimes more. Okay. Up to 2009 or so, all TI compilers supported a single ABI called the COF ABI, and we call it COF ABI because the object file format that was part of it was termed COF. Starting with the 470 compiler version 4.4 and C6000 version 7.2, we introduced EABI. And it stands for Extended Application Binary Interface. The build option you put out to trigger it is --ABI equals ABI. An important point to understand that is impossible, technically impossible, to mix COF ABI and EABI. There's no way to convert between the two. If you want to adopt EABI and you're presently using COF ABI, your only method is to rebuild from source code. Okay. Now, I understand a lot of you're obtaining libraries from other vendors or from some other part of TI. If you want to go off into EABI, step number one is to make sure that you can obtain EABI versions of all your libraries. These days, especially for C6000, that's easily done. And it's becoming less and less of an issue every day, but it's still something you need to take the time to check on it. There are, as always, there are details on the wiki about things like this that are undergoing change. There's an article there for C6000 and another one for ARM about EABI. And if you want to get into that, that's the first place you ought to go. Intrinsics versus assembly. All right, so to set the stage on this, if you want to program at a lower level of abstraction than C, one of the ways to do it is to say, I want to inject a little bit of assembly language into this function right here. And TI does support that with these limited ASM statements. They're not like the GCC ASM statements. GCC ASM statements are fairly intelligent, and they allow a fair amount of interaction between the C environment and the assembly language level environment. That is not the case with TI ASM statements. You can inject some assembly language, but you can't really interact with the C environment in any obvious and safe way. It's something that we really recommend that you do not do. Only as an absolute last resort would you go to something like this. We prefer if you use something called intrinsics. Now, intrinsics look and smell and act like a function call. Okay, it's just a function call with some special properties associated with it, and the main special property is, well, how is it implemented? It's usually implemented in a single instruction. Okay, so it doesn't, you don't actually call a function and pass arguments and get results back and all this. Usually it turns into a single instruction. There are a few exceptions, but the overwhelming majority of these guys are a single instruction. So, what's the big deal here? Why are intrinsics even being considered? Well, remember a few slides back we were talking about optimization and instruction scheduling and things like this. When the compiler is doing those operations, it's doing it because it knows an awful lot about the instructions being moved around. With regard to instructions and ASM statements, it knows basically nothing. It has to be very, very, very paranoid about what could be going on in the ASM statements, and this can impact your optimization. The exact opposite is true of intrinsics. An intrinsic is something that the compiler knows absolutely everything about. It knows as much about that intrinsic as it knows about any other instruction that it emitted just for a normal C expression. So optimization with intrinsics is far, far more effective. Okay, so this slide sort of sums up TI's position on this topic. Types and alignment, the one area where beginners tend to have the most trouble. So I start this section with this chart. The first column is just the names of the types in C, the base types in C. And then each column is how many bits wide is that type for that target. Okay, C28X is the first one, and so on. If something is shaded in gray, it's unusual. Okay, it's worth paying attention to because that particular width is different than what most people expect. You'll see 470, for instance, has no gray. Those are the sizes that people are used to. When you did your computer programming in school, those are the sizes that corresponded to your Intel laptop or whatever hosted whatever hosted system you were working on. So anytime it's gray, it could be a problem. On C6000 EABI, the size of long is 32 bits, and I do have a slide about that later. All right, so what are some of the consequences of these type differences? All right, so char is 16 bits wide on C55000 and C28X. This means that size of int and size of char are equal to each other, and they're both equal to 1. Kind of redefines the term byte. The term byte is an industry standard term, something that TI can't control, and applying it in these cases can be a little bit confusing because some people think byte means exactly 8 bits. Other people think byte means whatever size, the smallest size thing that the CPU can address. And most of the time that's all the same thing, but on these two targets it's not. And the interpretation that holds in that case is one that's less common, which is byte refers to the smallest thing that the CPU can address, which is 16 bits on C5000 and C28X. The main upshot is if you're trying to interface with an 8-bit wide external stream, something coming off the network wire, you have to handle that very, very, very carefully. It can be done. There's an app note right here that talks about the details if you're in that situation. Another thing to consider is for you 470 and MSP 430 users out there, the plain char type is unsigned. This is allowed by the ANSI standard. There's no reason you can't do this, but it is a little bit unusual. Most of the time, char is a signed type. What it really comes down to is it's okay to use the plain char type when the data that you're operating on is always, always, always nothing but ASCII chars, ASCII character values, okay, the printable ASCII character values. If it's anything else, could be any other kind of data, you need to be explicit about the signedness of your char. And this is true in general. This just isn't true for these two targets. This is something you really ought to do no matter what processor you're programming for. Floating point is very slow in CPUs without hardware support. If floating point speed is something that's important in your application, then you need to look into whether the CPU you're using has floating point hardware instructions. If it doesn't, then floating point operations are supported, but they're done with out-of-line runtime support calls. And so something like a floating point divide, you're looking at 100, maybe 200 instructions. Okay, so you need to be aware of that. A note on MSP 430, and actually that compiler has come out. If you've got the most recent version of it, long is a 64-bit wide type, and double actually is 64 bits wide for EABI under MSP 430. But that just came out, so this slide has not been updated as to that detail just yet. This is among the things that you would see in the Readme file, and that's why one of the first things I talk about in the slide says go read the Readme, so that your information is more up to date than even what you have here. The next slide, standard integer typedefs. This slide is really talking about there's a standard header file that comes with TI compilers that isn't commonly known, called standardint.h. And the purpose of standardint.h is to find these standard names for exact width integer types. And you see them right there, int16t, uint16t. The names are pretty obvious as to what they mean, signed 16-bit wide type. And you can see that the C type for it is int on some of our processors, and it's short on others. If you include this header file and use that type name, you make yourself independent of it. And I, in fact, highly recommend that if you don't use standardint.h, you do use this technique to some degree. It gives you a chance to get a hold of all your type names and handle them intelligently. In general, you want to avoid using just bare int, long, char, whatever in your code, and you want to use well-defined type names. And if you don't have any at all, I highly recommend that you start in with standardint.h. There are other types defined in that file for minimum width and fastest type that's at least this size and things like that. But the most popular ones by far are the fixed width ones. So don't go off and define your own. Use these. Okay, the promised slide on C6000 EABI and the size of long. Okay, so under COF ABI, long is 40 bits wide. Under EABI, long is 32 bits. And the reason we made the change is to ease porting of general purpose code from, laptops and whatnot to C6000. Code that people have long thought long was 32 bits wide. Well, if you build for EABI with C6000, it will continue to be 32 bits wide. Now, this does pose an issue for people who have existing C6000 code, and they built it under COF ABI, and they need a 40-bit wide type. Now, the answer for you is to, step one, while you're still under the COF ABI, change all instances of long to int40t. Okay? Get your code working, make sure it passes all your test vectors, this kind of thing, and then when you port it to EABI, guess what? It'll work the same way. Okay? So that's how you handle that. Alignment and structures. Alignment is talking about, what is the alignment of an int or a long double or whatever the case may be. On x86 systems, the processor running inside your laptop and your desktop PC and this kind of thing, if you do a misaligned access, say you access a 32-bit long on a boundary that is not a 4-byte boundary, it will work. It imposes a cycle count penalty. I don't know what it is, 2-3 cycles, something like that. But it will give you the right answer. If you do that with a TI processor, it'll just silently fail. There won't be any diagnostics, no messages, no nothing. You'll just silently get the wrong thing. Okay? So that's probably the first thing worth knowing. What is the alignment? Most of the time, the alignment is equal to the size of the type. Okay, so if it's a 4-bit wide type, the alignment's 4 bytes. There are a few exceptions to that, so consult your documentation, but that's a general rule of thumb that's fairly reliable. This becomes important in structures. Okay, if you got a structure and several, fields in the structure with whatever the types are, the order of the fields within the structure is guaranteed by the ANSI standard, but there might be gaps between the fields. Okay, and where those gaps are and how big those gaps are is not specified in the ANSI standard, and so the actual data layout of any given structure is not reliable. Okay, so this really affects exchanging data with external sources. This is actually, if I were to get all into it, I can almost spend 30 minutes talking about, well, why is this, and what are different techniques for addressing it, and things like this. But at this point, I just want to introduce you to the issue and make you aware of it. Pack structures are one way people try to, make structures more uniform. And without looking too much at the details of this slide, just to give you an overview, pack structures is a feature that we are adding into TI compilers. It's slowly rolling out. Some compilers are better support than others. And in fact, this slide is not entirely up to date anymore because it has improved even since then, and it will continue to improve. But starting with those compilers, the ARM and C6000 of those versions, and for ARM only if you're building for Cortex, and on C6000 if you're building some of the older processors, it's not supported. Details on all this are on that link right there about the GCC extensions, because we do employ a GCC extension as a syntactic method for indicating that a structure is to be packed. And a packed structure, basically, when I talk about the gaps between fields in a structure, those gaps will go away. There won't be any gaps. Everything will be, right next to each other. But for all this to work, the underlying hardware needs to support unaligned access. And so ARM Cortex, for instance, does support that. The more recent versions of C6000 do have some instructions that have, as a net effect, an unaligned load. We do have plans for relaxing this restriction over time, and so that is coming out. And I think the latest version of the MSP 430 compiler does have support for packed structures, But again, check the README before you depend on that. (16 by 16 to 32-bit multiply). All right, so this is a common operation in C. You want to, in digital signal processing. You want to multiply two 16-bit values and get a 32-bit wide result from it. And it's natural to think that you could write it the way it's written in this first case here, under this first bullet, like that. Well, guess what? That doesn't do what you think. I don't have time to break it down for you, but I will tell you that if you write it the second way right here, it's going to do what most people expect. Okay? This is particularly important on the processors where size of n is not equal to size of long. So C5000, C28, things like this. Oops, excuse me. Hit something I shouldn't have. This second way of writing it accurately represents the operation you're trying to carry out, and it is implemented efficiently. There's not an out-of-line call to a runtime support routine or anything like that. If you want to know all the details on this and why does it work this way, there's an app note about it right there, that SPRA 683. Memory models. Okay, so this first slide, I'm just sort of introducing some conceptual information, nothing target specific yet. Presuming you have some theoretical large memory model and some theoretical small memory model, what are some of the properties of those things and how are they different? Well, under large memory model, the memory range is, the full range of the device, however much memory it can address, whereas under the small memory model, it's going to be some lesser amount. Code size of a large memory model code tends to be bigger than small memory model code. You tend to pay a speed penalty for doing it, and that's why most of the time the default is small memory model, and you have to throw some compiler switch or another to enable large memory model, or you might have to use a keyword such as far or something like this. That's why I say see documentation for the details. So here's a little bit of the detail, and again, I'm really just trying to introduce you to the topic so that you you know to anticipate it, and you have a little bit of an idea of where to go and how to get started on it. But this isn't going to give you everything you need to know to actually efficiently operate with it. On C6000, there's a larger code model because of how the PC relative branches work. Now, you don't have to worry about this much in practice with C6000. We've managed to figure out a way to sort of handle it for you behind the scenes, but that is going on, and in rare cases people do get involved and try and overtake it and try to do something that's perfectly tailored to their situation, but most people tend not to worry about it at all these days. On C6000, again, the default data model works really well for most people, but it's probably a little bit more common for C6000 for you to require the far data memory model. And the reason why this is going on is that under small memory model, the way it works is that there's this data page register, and then there's a 15-bit offset from it. So you get, 2 to the 15th bytes past that register, the base address of that register, and that's the limit of what you can access in data on global variables. So that's the story there. It's a similar kind of story with the rest of them. C55000 under data, there's a large and small data memory model. That's because there are two different ways to access globals, and two different sizes of address registers. And if you start using the bigger ones, you pay a cycle count and a code size penalty for doing that. C28X is an extension of the data memory model. Again, two different sizes of address registers. On the MSP430, there's a different code and data model. There's a wider ALU, arithmetic logic unit. That's a portion of the CPU. And there are special instructions for using the wider ALU operations, but they cost you, so something to be aware of there. There is a wiki article on the C6000 data memory models. If you really want to understand all the details on this and why does it work that way and why is the default what it is and that kind of thing, that wiki article will walk you all the way through it. Compiler diagnostics. All right, so this first slide talks about diagnostics at a fairly high level. Diagnostics come in three varieties: remarks, warnings, and errors. And this table shows you some of the differences between the properties of those three kinds of diagnostics. The severity of a remark is low, warnings medium, errors high. If you get an error that will cause the build to fail, think about missing semicolon, for instance. You can't continue after that. Remarks are not enabled by default, but warnings and errors are. And then I pose the rhetorical question here: is it okay to ignore remarks? And this slide makes the point that no, you should not ignore remarks, because it gives a nice little example of a remark exposing a common bug. So that first little bar in yellow there, it's a complete program. I squeezed it all in one line to make it fit on the slide, but it's just main, invoking hello world, printf. If you actually try and run this, you'll get no output at all usually, if it doesn't crash or something worse. And so you want to know, well, what's going on here? Well, if you build with -pdr, or I think it's --issue remarks is the long form, you'll see this diagnostic right here, the line 1 remark function declared implicitly. What's really going on is that you're calling the printf function without giving a prototype for it. And this becomes important in the case of printf. Printf is what we call a variadic function. You can pass a variable number of arguments to it. Functions like that get special handling in the compiler. The way the arguments are passed to it is done in a special way. If there's no prototype visible, the compiler presumes that the arguments are passed to the function in a normal fashion. Well, that's not the case, and so the printf code, that actually lives in the runtime support library, expects that the variable argument conventions are being used, and if you don't use them, well, then basically the arguments don't get passed to printf is the net effect, and things just go downhill from there. So I'm just trying to make the point, you really want to build with remarks enabled, and you want to take the remarks seriously because it can help you find problems just like this one. In this particular case, the fix is to include standard.io.h. It includes, among other things, the prototype for printf, which tells the compiler that printf is a variadic function. And while we're talking about prototypes, you really should supply prototypes for your own user functions as well. Now, remember the default handling of remarks is it does not cause the build to fail. You can force a remark to cause a build to fail, and this slide talks about how do you do that. So you use two separate compilation steps, okay? The first compilation, you use -pden -pdr to see the remark number, okay? So on this hello.c, or here you see this 225, that's the number we're talking about. I got it in red. On the second compile, you use PDSE, then you put the number in to elevate the remark from, just remark handling to error handling. And so if you build that one-line hello world example with PDSE 225, you get this right here, the build will fail. Okay. Now, you can use PDSE 225 without -pdr in all your builds. And if you're a CCS v4 user and you start a project from scratch within within CCS v4, among the things that will be the case is the option -pdsw 225 will be set for you. So for projects started from scratch in CCS v4, the handling of functions declared implicitly is they are a warning. So you'll see them, but it won't cause the build to fail. If you want to change that, now you know how to do it. This next slide builds on that even more. It makes the case for you can change the handling of any what we call discretionary diagnostic. If you see, when the diagnostic comes out, if you see a -D as part of the number, that says it's a discretionary diagnostic. And it's easier to talk about this by talking about a counterexample first. Missing semicolon is not discretionary. You don't get the option of lowering missing semicolon from an error to a warning or anything else. That's always an error no matter what. It is not discretionary. But all warnings and remarks are discretionary, and it's possible for you, the user, to control how the compiler reacts when those diagnostics are issued. You can use build options like we did on the previous slide. We use PDSE 225. There's also a pragma that you can put in a header file or in the C source to do the same thing. Probably the interesting one worth pointing out here is pragma diag default right there. That will reset that particular diagnostic back to its original level. Okay, so that's for the case where you want to temporarily change the handling of a diagnostic for a one function or a few lines or whatnot, and then you want to set it back to its normal handling. You can say like pragma diag error, whatever the number is, have a couple of lines of source code, and pragma diag default. If you want to see this in detail, there are some slides in the backup section of this slide set where it gives you an example of doing that. I'm not going to have time to go through it in this particular run through the talk. All right, some useful utilities. So now we're going to stop talking about C compilers and assemblers and linkers and talk about a few other things. So these are bundled with the compiler package. They're in the same bin directory as C06X and everything else. You see these capital X's here, XX. Change that to the abbreviation for your instruction set architecture, so OFD6X or NM55 or whatever it is, okay? OFD dumps out the contents of your object files and libraries, and you can use -X to get that information in XML format. NM55 or NMXX will dump out the symbol table. You can do some interesting things with that. In some rare instances, you need to strip out the symbol and debug information from an out file or an object file, and you can do that with the strip utility. You C++ users out there, the linker map file and other files of this form will show the mangled function names, and if you want to see it back in the original way it was written in your C++ source, you need to use a demangler. And then there's a disassembler for some of our architectures, not all of them. If you want to look at a piece of object code or an out file that maybe you didn't write or you did write it but you want to see how it was really done after all the pre-processing happened or whatever, disassembler is the tool for you. Even cooler utilities, okay. So I mentioned that you can get object file information in XML format. It turns out you can also get the linker map file in XML format. And then there's a package called the CGXML package that includes utilities that operate upon those XML files and give you all sorts of interesting information. You can see the call graph, who called who, how much stack is actually getting used. You can see what is the total amount of code size and data size and uninitialized data size in your out file, and things like this. The package does not get released with compilers, released independently. If you're interested in command line executables, this is a link for you right here. You can also invoke CGXML utilities from within CCS v4. You have to get the command line package, and then you also get this plugin for CCS v4, and then you can do it that way. So, last few remaining tips. This is just a collection of things that I'd like you to know, but I didn't have a neat place to put them, okay? C++ code is usually very efficient in the hands of experienced practitioners. If you're brand new to C++ code, it is certainly possible for you to write code that performs poorly. But if you take the time to educate yourself on the issue, you can do a really, really good job. Educating yourself on the issue is usually a book-length enterprise. There's a couple of books by, can't think of his name right now. But there are some books on this topic. I need to put the names of those books in the slide, to be honest with you. But that's really where that kind of thing lives and dies. It doesn't live and die in the TI C++ implementation or any other C++ implementation. It's in the language itself. There are correct ways of doing things, and then there are wrong ways of doing things that beginners tend to fall into, and you need to know what those are and avoid them, okay? The pragma directive, it's a preprocessor directive, is compiler specific and doesn't port, okay? If you're using pragma directives and you expect them to do a similar thing in the next compiler that you run your code through, you might get a rude surprise. There's a wiki article that talks about that. And for those of you who are even experienced people at C and C++, I often answer questions with a reference to something within one of these FAQs, the C FAQ, the C++ FAQ. I think they're worth just looking through in general. You can learn some things that are like, wow, I didn't know that. And it can be interesting stuff worth knowing. Okay, so I usually give this talk live, and this is the point where I ask for questions from the audience and we field them and things like that. But we're not going to be doing that here, obviously. And I'm not going to go all the way through the backup slides in this case, but I will show you the backup slide agenda just to give you an idea of what else is in here if you want to come back and look at the slides themselves. The slides are available from the compiler wiki that I mentioned, but on slide number 2. There's a article called Tips and Tricks, and that contains this slide set, and that's where you can get these slides. More optimization hints, just a little bit more information about using the optimization part of the compiler. Standardized handling of types. In addition to standard int.h, there's another header file that you can do some interesting things with. More examples on how you can use the diagnostic abilities of the compiler to avoid problems in your code. C headers in assembly talks about how you can have information in a header file in C and refer to it and use it in your hand-coded assembly. Okay, that's what's going on there. Interrupt intrinsics. We already talked about what intrinsics are. There are some intrinsics related to enabling and disabling interrupts, and there's a kind of a right way and a wrong way to go about that using the intrinsics, and it talks about that. And then the last agenda item, predefined symbols for version. This is a preprocessor symbol that contains the version number of the compiler that you're presently using, and what can you do with that. So that wraps up this recording of this talk. Again, my name is George Mock, and I hope you found this useful. Thank you very much.